We are now ready to generalize Euclidean geometry to infinite dimensions, namely to Hilbert spaces. The advantage is that we have an intuition from finite dimensional spaces, and all the notions like vectors, inner products, angles will carry over, and we just have to be a little bit careful of what happens when we go to infinite dimensions. The K notions are, as announced, the length of a vector, which has to be finite, the angle between vectors, which we can measure with inner products, and bases for these infinite dimensional spaces, which are called Hilbert spaces. Module 3.2. After this introduction, where we essentially showed everything by hand with little examples in R2, giving the intuition when we generalize the vectors from Euclidean vectors to vectors in Hilbert spaces, let us be a little bit more formal and define things in a proper way. This will be the definition of Hilbert spaces and a set of examples. So what are the ingredients of vector spaces or Hilbert spaces? So we need a vector space, which is a set of vectors. So V is a set of vectors. Okay, it will be a countable set. So maybe it's finite dimensionals and K is some finite set, or it's infinite dimensionals and it's an index of integers. And we have a space of scalars. Typically it's going to be complex numbers. Okay, then we need an inner product. That's a map from the two vectors, so two elements from V, that maps into a complex number. And finally, we need something a little bit technical, which is called completeness, which we will explain with an example. We need two ingredients to do operations. The first one is called multiplication by a scalar. That's the first operation. And we need to be able to combine vectors together, which is vector addition. Let's see this very concretely again in R2. So our vector x has entries x0 and x1, as always. This is our vector, the origin. This is the coordinates x0, x1. Scalar multiplication is very obvious. You multiply by, in this case, by 1.5. You get a new vector, longer. It, of course, is collinear. It's exactly the same direction. It's simply a longer vector, so the norm has changed by a factor 1.5. Addition of vectors. So we have our two vectors, x and y. The sum is, we put y on top of x, and we get the sum here, x plus y. Okay, in terms of coordinates, very obvious what's happening. You add the individual coordinates, x0 plus y0, x1 plus y1. As we said, vectors can be very general. So let's do the same with now continuous time functions. Here we have sine of pi t between -1 and 1, as usual. If we multiply it by 1.5, we get this new thing here, which is 50% bigger. If we add two vectors, let's start with x, which is our sine pi t. Let's look at y, which is sine 5 pi t. Okay, it's the orange thing here. We add the two together. It is a blue function. Okay, it's a new vector, which is simply the addition of the two vectors. And it's easily verified visually, actually, that this is the sum of the two previous vectors. The formal properties of a vector space. I apologize in advance, this is a little bit dry. It's a laundry list of properties. So the first one is that vector addition is symmetric or commutative. The second one is that addition is distributive, that we can add in any order here and it will give the same result. Then scalar multiplication distributes over vector addition, so alpha times x plus y is simply alpha y plus alpha x. It's the same in the reverse order, so alpha plus beta, so that's a new scalar, times x is alpha x plus beta x. Then we can see that alpha times beta x is indeed alpha beta x. All of these are very obvious for finite dimensional spaces. Finally, there is a 0 element in the vector space, that's the origin, so x plus 0 is equal to 0 plus x is equal to x itself. And there exists an inverse, so if we have a vector x, there exists in the vector space a vector minus x, so that the sum of the two is equal to the 0 vector, or the origin. Okay, so if we have this, so we have vectors from a vector space, scalars from complex numbers, and these properties, then we have formally a vector space. If we have a vector space, there exists subspaces. The intuition is that R2 is a subspace of R3. We had seen this graphically in the previous submodule. And the way to find or verify that we have a subspace is simply that addition and scaling in the subspace must remain in the subspace. All the other properties from the previous slides are automatically inherited. Okay? So the example again is easy in R3. So if we have in R3 with basis vector E0, E1, E3, if we add two vectors in the subspace R2, which is the floor, if you want, in this three-dimensional space, then y plus x plus y, two vectors in R2, the result will be a vector in R2. Okay, and just to make sure, R2 here is spanned by E0, D1. This again holds for more general vectors. Let's take here the subspace of symmetric functions over the interval -1 to 1. So one example of a symmetric function is cosine pi t. Another example is cosine 5 pi t, also a symmetric function. Sure enough, the sum of the two is a symmetric function. It's a blue function here as a result. On vector spaces, we can define inner products. And inner products measure the similarity between vectors. Okay, we'll make it precise in a minute. But when an inner product is 0 between two vectors, then it means the vectors are orthogonal to each other. Okay? So what I'm also saying here is that the similarity is also measuring both the similarity in length and the angle between vectors. Okay? All right, so let's look at an inner product in R2. The definition is very simple. The inner product between x and y is equal to the sum of the term-wise product, so x0 times y0 plus x1 times y1. So in this case, for example, we have x, we have y. The inner product can be rewritten. I'm not going through the algebra that does this, but it's a simple exercise which I suggest you actually do on a piece of paper. Then this expression is equivalent to this one, which is interesting in the following way. This is the angle between the two vectors. This is the product of the lengths squared, taken a square root. So this is simply, we are going to see it's equal to the norm of x times the norm of y times the cosine of the angle between the two. Okay? This is a very important formula that we'll see a couple of more times in this class. Okay, when two vectors are orthogonal to each other, alpha being equal to pi over 2, then the inner product is exactly equal to 0. We can go back, of course, because cosine of pi over 2 is 0, the inner product is 0. Okay? You can also verify that this will be the case in this formulation. Okay, the two are equivalent, and while in the formula which includes the cosine, it's obvious, in the other one you have to do the algebra. Now this inner product can be generalized to continuous time functions, sure enough, no surprise. So let's take two vectors, our good old friend sine pi t, and another vector y. in this case y is equal to t, and we are going to calculate the inner product. In this case, the definition is that it's the product of the two functions, xt times yt, integrated over the interval -1 to 1. Okay, so that's the definition of the inner product for this space. That's a space we call L2 of -1 to 1. The interval -1 to 1 in the space of square integrable functions on that space. Okay. If we do this, let's take the two vectors, y and x, the product, which is the blue function here, and we can take the integral. Let me take the integral and, well, doing a little bit of trigonometry, you integrate t sine pi t between -1 and 1, it will be equal to a positive number that we can see here graphically, because the product is both positive on the negative half and positive on the positive half. Then you integrate this blue function, and indeed you get something that is positive. It happens to be 2 over pi. If you take the inner product of x with itself, so x is sine of pi t, then we can verify that the inner product with itself, so that's the inner product of sine square between -1 and 1, well, the square is this blue thing here, and the integral will be exactly equal to 1. So x, okay, inner product with itself is actually equal to the norm square, and it's equal to 1. Okay, so we have a vector sine pi of t that is of length 1. Okay, if you take inner products between vectors that come from subspaces that are orthogonal to each other, then, as you may guess, the inner product will be equal to 0. So we show this in the following diagram by taking an antisymmetric function, that's our friend sine pi t, and a symmetric function, which is 1 minus the absolute value of t, so the absolute value of t, 1 minus the absolute value of t starts here, goes down to 0 at the two ends, okay? We also call this sometimes the hat function, because it does look a little bit like a hat, and it's clearly a symmetric function. So the orange function is symmetric, the red one is antisymmetric. The product will be negative on the first half, positive on the second half, have exactly the same surface here, that when integrated out it's equal to 0. Okay, so these two vectors here, x and y, are actually orthogonal to each other. Okay, now we see a geometric properties that is very obvious in R2, and here it happens for much more general case of continuous time vectors. Now let's look at a case of vectors that is very important in signal processing, and these are sinusoids. And we again look at sinusoids here over an interval, -1 to 1, and the first vector x, which is sine of 4 pi t, and another one which is y is equal to sine 5 pi t. So you can see that these are integer multiples of a fundamental frequency, which is pi. And what is not obvious by looking at this at first is that these two vectors also are orthogonal. So I'm going to write it down because we're going to verify it. Okay? So I claim that the inner product between x and y, with these expressions, the inner product is going to be equal to 0. Well, let's first calculate the product of sine 4 pi t and sine 5 pi t. This product is given by the pink or green function depending on the sign of the product. Okay, sometimes the product is positive, sometimes it is negative. And now we have to integrate this out. And if you watch this very carefully, you will see that positive and negative terms cancel each other very nicely. So this was clear. This fellow here cancels that one, this fellow cancels that one, this fellow cancels this one. And so this integral is 0, and the other side is exactly the same story, and you have always cancellations. So overall, this integral or inner product is equal to 0, and we have thus verified that x is orthogonal to y. Okay, now we did this graphically. You can go through the trigonometry, do the integrals, and figure it out. It's a good exercise. But the main message is that here we have verified an orthogonality property for harmonic signs. Okay, this inner product that we have seen now, it was in finite dimensions, very simple. It's also called a scalar product. Sometimes in continuous time, it's the integral of the product of two functions. Let's look at their formal properties. Again, it's a little bit of a laundry list, so bear with me for a minute. So we have three vectors from the vector space and a scalar from the complex numbers. So the inner product will satisfy linearity in the various arguments. So if we take inner product of x plus y, inner product with z, it's equal to the inner products, the individual inner products summed together. If we look at the inner product of x and y, it's equal to the inner product of y with x, but with a complex conjugate. Okay, and if we scale the left side vector by alpha, it's the same as multiplying the inner product with alpha complex conjugate. On the other hand, if we multiply the second element with alpha, it will multiply the inner product by alpha. Please note that different communities decide to allocate the complex conjugate either here or there. It's a little detailed, but when you read papers, you may want to pay attention to this. Then the inner product is always greater or equal to 0, okay? Because in some sense it measures the length of a vector, and the length of the vector is necessarily either 0 if the vector is equal to 0, or it is a positive number. Okay, which is said here. So if the inner product is equal to 0, it means the vector is actually the 0 vector. Finally, if the inner product of x and y is 0, and x and y are different from the 0 vectors, then x and y are called orthogonal to each other, which we always denote here with this shorthand for the right angle. Okay. Now let's look at inner products for signals. So signals are discrete time sequences. So the definition for the inner product of a finite length signal, or a vector of length capital N, is given here. It's simply the sum from 0 to n minus 1 of the first entry x star, so complex conjugate of the first entry, times the second entry. So this is also sometimes called a scalar product in Cn. Or to make a very little example, if I have two vectors, x0, x1, and so x is this guy, y would be y0, y1, then the inner product is simply the scalar product x0 star, x1 star, times y0, y1. Okay? This is exactly the formula up there for n is equal to 2. Alright, if we look at infinite sequences, the expression is the same. The only difference is that now we have to sum from minus infinity to plus infinity, and since it's an infinite sum, unless these sequences are of sufficiently fast decay, meaning when n goes to infinity that they go fast to 0, this sum might actually explode. Okay? When the sum explodes, then the inner product is not defined. Okay? We don't like inner products that go to infinity. Okay? And so our spaces of interest will be the space of vectors where the vectors themselves have finite L2 norm, and therefore their inner products have also finite L2 norm. Or sum of squares are finite. Okay? This is what we say here. We have a requirement that sequences are square summable. This is this requirement here. Okay? This will guarantee that the inner product will not explode, and the space of square summable sequences we denote by small l2 of z. Okay, why small l2 of z? So small l means it's sequences, the 2 means we are interested in the square norm, this thing here, and the z means we are interested in the set of integers, so that's the index set for the sequences. Okay, so this is a very important space. Essentially, most of the things you're going to do in this class deal with the space L2 of z, the space of square summable sequences. Now, the inner product defines a norm or a length by taking the square root of the inner product of x with itself. Okay? It also defines the distance between two vectors, so the distance between x and y is simply the norm of the difference. Okay? And let's look at this in R2 as usual. So the norm of x, square root of the inner product, of course, is simply the square root of the first entry squared plus the second entry squared. Very natural. Okay, so we have x, we have its norm, we have y, we have its norm, defined the same way, and we have the length of the difference here, the norm of x minus y, which is the distance between the tip of the two vectors. Again, the very same notions extend to continuous time functions. So, for example, for continuous time functions on the interval -1 to 1, our usual friend, let's take two vectors, x, which is sine of pi t, y, which is equal to t, then the square of the difference is simply the integral for -1 to 1 of x minus y absolute value squared. Sometimes this is called the mean square error between these two functions. Okay, so let's calculate it. So x is the red sine wave, orange is the function t, the difference is this blue thing, the square of the difference is this this surface here, as you can see, and the integral is going to be a positive number very clearly, okay, because the difference is different from 0. You can do the trigonometry again, it's nothing very fancy, but we know graphically that it's going to be strictly bigger than 0. Now we're going to discuss a very familiar result, which is called the Pythagorean theorem. The Pythagorean theorem that you probably know from the two-dimensional incarnation says that when two vectors are orthogonal to each other, so x is orthogonal to y, then the norm of x plus y squared is equal to the norm squared of x plus the norm squared of y. Now, we mention this because it goes back to the ancient Greeks, actually probably to the Babylonians and so on, and there is a very beautiful illustrated version of Euclid's Elements by a British statistician, Oliver Byrne, from the 19th century, who essentially redid all the proofs in Euclid's Elements, so that's a 2,000-year-old book, with graphical proofs, for example, of the Pythagorean theorem, which is actually given here. It's one of the many proofs of the Pythagorean theorem. Okay. Knowing the Pythagorean theorem is very useful. Having basis for R2, R3, or for that matter, Hilbert spaces is also extremely useful. Okay. So when we have a basis, then any vector can be written as a linear combination of the basis vectors. So let's take an example. Let's say that x is 2, 1, the 2, 1 vector, and it can be written as 2 times the first basis vector. Okay, first basis vector is here, plus once the second one. Okay, so 2 times this character plus once the other character indeed reconstructs x. Okay. And we can also do this more generally with two vectors that are not collinear, so they are linearly independent, like v0, which is equal to e0, v1, which is equal to e0 plus e1. And we can also write any vector as a linear combination. unless we take two vectors, for example g0 and g1, which are collinear. Okay, so there is no way to write x as a linear combination of g0 and g1, because these guys are actually linearly dependent. Actually, the sum of g1 plus g0 is equal to 0, okay, which shows that they are linearly dependent. Okay, so here we have seen two cases. If I may go just back for a second. One, it was an orthogonal basis, E0, E1. The second one was a biorthogonal basis, V0, V1. The third one was no basis at all. It was two vectors that were collinear or linearly dependent, and these are useless to represent a general vector in R2. Okay, so more generally a basis is given by the following properties. We have a vector space H. We have a set of k vectors from H, denotes them by wk, with k going from 0 to k minus 1. W is a basis for H if we can write all x's in H as a linear combination of the basis vectors, and the coefficients alpha k are unique. Here we discussed a finite dimensional case. H is of dimension, the dimension of H is equal to k. Okay? The unique representation condition we saw on the previous slide actually implies linear independence. Linear independence means you have a set of k vectors. This equality, so if you can write the sum of the vectors equal to 0, this implies that all the coefficients have to be exactly equal to 0. And then that's a test that we have linear independence of the vectors. Among bases, a very special one is the orthogonal basis, or even better, the orthonormal basis. So for an orthogonal basis, we need a set of vectors which are mutually orthogonal. This we can write by saying that the inner product between any two vectors wk, wn is equal to 0 when k is different from n. And then we can get an orthonormal basis when the individual vectors are actually normalized, so they have a norm equal to 1. And this is conveniently written here by this formula. So the inner product between wk and wn is equal to delta n minus k. Now, the delta sequence that we have seen, let me just remind you, delta of n is equal to 1 when n is equal to 0 and it's equal to 0 else. And so this formula here means that when n is equal to k, then this is equal to 1. So the vectors are of norm 1. And when n is different from 0, the vectors are orthogonal. If you have a basis which is not an orthonormal basis, you can always orthonormalize it using a procedure that is called the Gram-Schmidt algorithm. You might have heard about this algorithm, and we will review it a little bit later, maybe not in too much detail, because it's a fairly standard algorithm in numerical linear algebra and approximation. Now, if we have a basis, how do we get the expansion factor? So if we have a basis, it means any vector x can be written as a linear combination of the basis vectors. Okay? The only thing we need is to find out what the alpha k's are, the coefficients in the expansion. Okay? So how do we find these alphas? Well, in the case of orthonormal basis, it's very easy. The alpha k is simply the inner product of the kth basis vector with the vector we want to expand. Okay? Let us see this in the simplest case, which are bases for Cn. So we are in a finite dimensional space, so a basis will have exactly n vectors, since we are in Cn. And the canonical orthonormal basis is simply the basis of indicator vector. So Ek has a 1 in the kth position. So E0 would have a 1 here, E1 here, etc. Okay? And this is, a bona fide basis for the n-dimensional space Cn. Okay? For sequences, we can do the same by simply putting a basis vector ek, which has a 1 in the k's position, but k now goes from -infinity to +infinity. Okay, that basis is actually infinite dimensional because, of course, sequences have an infinite number of terms. So these are the two very simple canonical bases, one for Cn, the other one for L2 of Z. Now there is one ingredient which is slightly technical that is still missing so that we get Hilbert spaces. It's so-called completeness. The reason we need this is that when we take limits, we would like to make sure that the limits of a sequence of vectors is still in the vector space. To show you why this is a requirement, we can give some intuition by showing an incomplete space. So the set of rational numbers, which is all the numbers, so Q, the set of rational numbers, is a set of numbers where we have a ratio A over B, where A, B are actually integers, okay? And that's a very rich set, right? It's doubly infinite because these guys are infinite, these guys are infinite, so it's a very huge set. But it is incomplete because you can write, for example, limiting operations. So let's say xn is a sum from 0 to n of 1 over k factorial. So each term, xn, is a rational number because it's a sum of here 1 over an integer. Okay, so k factorial is an integer, 1 over k is therefore a rational. And so each vector is a rational, but the limit of this sum as n goes to infinity is equal to e, which is an irrational number. Okay? And so you see that what's happening really is that we do this sum, and the term x1 is equal to 2, x2 is there, x3 is there, etc. But at some point the limit is actually an irrational number. Okay? And for those of you interested in this, that's one, of course, of the beauties of analysis, is that the set of real numbers is completely filled with rational numbers. However, there are these holes which are the irrational numbers.